Okay, so welcome again to the third lecture of the course Fundamentals of Solar Photovoltaics and Technologies. Let's briefly recap what we did in the last two classes. In the last two classes, we learnt about the importance of energy. Why is energy important? It has been important to us right from our evolution as a hunter-gatherer to a civilized man, wherein we moved on from just to hunt for the need of food or other activities to inventing materials, inventing technologies, and inventing variety of gadgets that we use in today's life. And starting from food to agriculture to development of materials and gadgets, everything requires energy. So basically, we need energy for almost everything that we do. And typically, energy was derived from fossil fuels. Initially, we used biomass, but then as the technologies developed, we started using coal, oil and gas, and all of these are fossil fuels, which means they took a lot of time or long periods of time to form, and we have been burning them, we have been excavating them and burning them for a significant period of time now. So the consumption of energy has grown as the populations have grown, and populations have grown because of improvements in healthcare, but at the same time growth in population is also related to growth in consumption patterns of people, and these consumption patterns are directly related to consumption of energy. As a result, we have been steadily increasing our consumption of fossil fuels, moving on from biomass. Now we have been producing significant amounts of oil, gas and coal, on which our current modern economy thrives. There is a downside to it. While burning fossil fuels provides us a lot of energy, employment, and it's a very big driver for economic growth. The downside is that burning of these fossil fuels leads to significant amount of greenhouse gas emissions, that is GHG emissions. And as we saw in the last class, that currently we emit more than 10 times of what we can naturally sequester on this earth. There are natural processes which can absorb CO2, but we emit which can sequester about 10 gigatons of carbon dioxide, but what we emit right now is in the excess of 50 gigatons if we consider all the greenhouse gases. And it is because of greenhouse effect of these gases which allows them to entrap heat in the outer atmosphere of the earth. There is significant amount of global warming, and this global warming is something which is paramount to what we see today in terms of consequences. So in this lecture, what we are going to do is that we are going to look at what the consequences are of incessant use of fossil fuels, and then what should we do as a civilization as the world continues to increase its energy demand. And this is especially important because we are now close to 8 billion, projected to be 10 billion in future, and this energy demand will significantly rise as the countries become more and more prosperous. So as far as greenhouse gas emissions are concerned, the most important thing about them is warming. The plot on the left shows, this is from IPCC report, it shows the atmospheric concentrations of long-lived greenhouse gases, and on the left hand side we see concentrations of carbon dioxide and nitrous oxide in parts per million and parts per billion, as well as methane, and we see that the concentrations of these gases in the atmosphere were relatively flat until about 1800 AD. And since about 1800 AD, when the Industrial Revolution really took place, they have been increasing exponentially, and today if we look at carbon dioxide, we are already beyond 400 parts per million, and as far as methane is concerned, we are beyond 1200 parts per billion, and same is true for nitrous oxide as well. So there has been a significant buildup of these gases, although these numbers might sound smaller, but in the context of environment these numbers are fairly big, and this tremendous buildup of these gases in the atmosphere has a lot to do with global warming because of greenhouse gas effects. And as I told you in the last class, that gases like methane and nitrous oxide, they have significant global warming potential, much higher than carbon dioxide, and these gases also have different residence times. In total, the world has about 75% of the total amount of gases that are built up in our outer atmosphere. 75% of that is carbon dioxide, and about 20% is methane, remaining is nitrous oxide and other pollutants. Scientists have noted over years that the average global temperature has already increased by 1.5 degrees centigrade. It has significantly accelerated from about 1900, and today as we stand in 2025, the 1.5 degree mark is already breached according to some reports. And this plot as our world in data, you can look at this website, fantastic website for look at different datas, and really shows that the temperature is already in the excess of 1.5 degrees centigrade. Now these are very conservative estimates. Of course, if you go by very aggressive estimates, the numbers could be even dire. This warming because of buildup of these gases has also, so it has given rise to warming, and warming has resulted in melting of glaciers and melting of variety of snow covers across the world, and this has resulted in sea level rise. So one can already see starting from 1880 until 2020, based on the documented data, that sea level rise is approximately 200 millimeter. These variations will vary, will change depending upon report to report, but this is one report that suggests that there is about 200 millimeter of sea rise that has already happened, and 200 millimeter of sea rise is significant. It's more than 6 inches of sea rise, which is catastrophic for certain countries which are very low lying countries, and many islands could submerge in a short period of time. So there are multiple consequences, not just sea level rise, but also reduction in polar ice. It has been documented that polar ice has reduced nearly by 50%, and this is something which has been documented, as the image on the right shows. Polar ice is very important for us because it helps to keep the planet cool, otherwise we will be very hot. So North Pole and South Pole, the ice cover has gone down. Melting of glaciers, many glaciers which used to exist 50-100 years ago, they are not visible anymore. There has been tremendous loss of biodiversity. Many of the species on the planet have become extinct, and some other can become extinct if we don't curtail the global warming in time. There have been recorded extreme weather events like floods and hurricanes, and it has been scientifically estimated that many of these events have become far more common than they were earlier. The rains and oceans have become certainly more acidic, and acidification of ocean is really a very dire phenomena which is bad for all the marine species that live in there, and we are also dependent upon marine species for our own living. Not only this, but we have also this kind of exploitation of natural resources has also led to pollution of natural resources, especially all the food and water supplies. Many of them are contaminated today, and all of these they have consequences for our own living, especially health consequences. The rising temperatures, the rising pollutants concentration in the atmosphere, they have significant tremendous health consequences for the human beings and other species of the planet. So you can see on the right the images, the top image shows the reduction in polar ice cover, but at the bottom image shows one of the examples of flooding that can occur in certain parts of the world. And this is about number of reported natural disasters. You can see from 1900 until today, the number of natural disasters that used to be far more smaller. Of course, a lot depends upon reported natural disasters. So earlier the populations didn't report it that frequently, but even if you take a conservative estimate, there is a significant increase in the number of natural disasters that have been occurring, especially since 1950s or 60s. This is also true for coral bleaching. The percentage coral loss for 1.5 degrees centigrade is 70%, but if you go to 2%, it will become 99%. Species loss again will be major casualty if we breach this 1.5 degree centigrade mark and go to 2 degree centigrade mark. Droughts will become far more severe, and many more people will get affected, and same is true for the sea levels, which will lead to displacement of a lot of people and re-establishment of infrastructure after the destruction of already established infrastructure. So problems are likely to aggravate if temperature rises further beyond 1.5 degrees centigrade, and that is why many of the climate scientists, IPCC and many other world organizations are gunning for reducing the emissions as far as we can. So greenhouse gas emissions in 1850, as our world in data shows, they were about 4.2 billion tons, and they were roughly similar to what we could sequester. And these include carbon dioxide, methane, nitrous oxide from all types of sources, including the land change used. And they are measured over a pretty long time, so about 100 years time scale. And this was directly related to fossil fuel uses, which is the direct cause of greenhouse gas emissions. And these greenhouse gas emissions have increased at a very rapid pace from 1850 until today, and today our greenhouse gas emissions exceed 50 gigatons or 50 billion tons across the world. And 2022, for instance, saw greenhouse gas emissions of 53.85 billion tons. And you can see the earlier in 1920, the countries that emitted most of this emission were US, Russia, China, and in India, but those numbers were smaller. Today, the major polluters of the world are, of course, China and US, and India is not far behind, although per capita emissions might be lower because of larger population of India. But nevertheless, the world has become much more browner than it was in 1850, and this increase in emission has to be curtailed. This is a picture of per capita greenhouse gas emissions. So you can see the picture changes a bit. Many of the countries which were appearing darker earlier, they become lighter because their populations are larger. So per person they are emitting less. And countries like Australia, Mongolia, Saudi Arabia, Canada, which are thinly populated countries, but they consume a lot of energy, they become dark red. But nevertheless, it's a global problem because there are no boundaries in the skies. As a result, everybody has to make their own effort to emit less. And this is especially important because it has been predicted that the world energy demand is likely to increase by 2050. So if you look at this plot, which is energy consumption by sector versus the year, here OECD means Organization for Economic and Cooperation and Development, which means mostly developed countries. India is not part of OECD group. You can see that for developed countries, the energy demand is going to remain fairly low in terms of quads. So quads is a unit which is written at the bottom. So one quad is equal to 10^15 BTUs or British thermal units, which is equal to 1.055 exajoules. So you can see that the demand of OECD countries is going to remain relatively flat, but in contrast, the demand of non-OECD countries like India and China and many other developing countries, this is going to increase very rapidly, becoming almost 2 times of what it is today, or maybe if not 2 times, then 1.5 to 1.8 times. And this is going to come from all the sectors. It is going to come from residential sector, commercial sectors, transportation sectors, and industrial sectors. Demand is going to increase, so the question is, what do we do? So a very important question is that we know that our energy demand is going to increase because we are going to become more and more prosperous. Our number of people is going to increase, which means our emissions, our energy demand will increase significantly. What should be our response? Should we continue to keep using the fossil fuels, or should we do other things? So that is where this concept of energy sustainability comes. If we want to grow sustainably across the world, which means we should not have future generations living in difficult situations. We need energy, but we need energy at the same time. So there has to be some alternative concept for energy sustainability which cannot be reliant on the use of fossil fuels. So larger populations with increasing prosperity will of course need more energy. So that is where there is a need for developing sustainable methods of energy generation which are non-fossil fuel based, so that we can minimize the greenhouse gas emissions, bring them below what currently they are, so that we can arrest the increase in global temperature, keep it below 1.5 or 2 degrees centigrade, and prevent the world from facing a catastrophe in the future. So that is where the most acceptable solution is that we must switch to renewable sources of energy which are non-fossil fuel based, which are abundant in nature, and which provide us energy by making fantastic technological innovations, but by producing significantly less emissions. So, there are multiple sources of renewable energy technologies. The first one is solar photovoltaic technology, which is based on use of solar energy and converting it directly into electricity. So, solar photovoltaic is a very important technology that converts solar radiation directly into useful electricity. Another method could be geothermal, because there are certain parts of the world the heat that is produced underneath the earth where we live can be used to produce energy in different forms, in the form of both electricity and heat, using different technology options. There is also possibility of converting a lot of biomass which otherwise goes to waste into electricity. Similarly, hydroelectric, the world has different topographies all across its surface, and these topographical or height differences across the world, especially in mountainous areas, can be used to store water at high heights and releasing them when we want to produce electricity, or to arrest the flow of water by creating check dams and releasing them when you want electricity. So, and other options could be tidal electricity. We have large coastlines across the world, so tidal and wave energy can be another option. And then finally, the wind energy, which is using the kinetic energy of the wind to convert that into electricity. So, we have multiple options. Question is which renewable or non-fossil fuel technology to choose. One option that is being contemplated for a very long time is nuclear energy, which is based on the fission of radioactive nuclei. Of course, it is a very good technology. It is not a fossil fuel based technology, but this technology requires large scale installations, although there is nowadays talk about small modular reactors. But to meet a demand of, let us say, 500 gigawatts for the world, we require 501 gigawatt reactors, which means there has to be one reactor every 1 month until 2030, which is a long ask. So, it is not going to happen by 2030, we know for sure, because there are certain regulations that have to be followed to install nuclear energy, and there are safety issues which have to be overcome. So, nuclear is an option, but it is not a complete solution. Wind is another thing. You can use kinetic energy of wind to convert that into electricity. There are a lot of windmills across the world, but wind speed is an issue in India. It is not high everywhere. You need a certain critical wind speed to convert into electricity. It is a good option, but it is limited in nature. Biomass is also an option, but it requires a lot of land, which is a luxury for India. Geothermal ocean waves, in the context of India, the tidal speeds are lower. As a result, geothermal also capacity is lower in India. Again, it has limited viability. So, in this context, it is the solar energy which becomes fastest growing renewable energy technology. You can convert solar energy into electricity using two methods. One is solar thermal, another is solar photovoltaics, and this is because solar energy is abundant. About 100 petawatts of solar energy or solar power hits earth. So, every second you are getting 100 petajoule, and yearly it amounts to an energy of about 3.4 million exajoules. This is very large in comparison to what we consume, and even if you convert 0.1 of this energy into electricity at, let us say, efficiency of 10%, you will produce 10,000 gigawatt of power, which is significantly larger than what we consume today. So, you can convert this solar energy into electricity using two methods. One is solar thermal, second is solar photovoltaics. Solar thermal is a nice method wherein you convert solar energy into first heat, and then heat is converted to steam, and then steam is then used to run the turbines, but it requires large scale installations, and so far its economics has been unviable, although there are some reports from China that this technology might become more successful in future. Second important technology is solar photovoltaics, which converts solar energy directly into electricity, and this is something which is talk of the town right now. There are many solar installations which have been happening right across the world. Current solar installations, the cost in India, for example, with subsidies have come down to about ₹3 per unit, and for grid connected electricity. And if you want to go for domestic solutions, which means you are non-grid connected, then you have to have inverter and battery storage, which means your cost will go up. So, to make the solar energy popular all across the world, we require even better technological breakthroughs, and this is mainly driven by research in materials and chemistry which are driving these innovations. So in this course we'll only be talking about the solar photovoltaics, which is one of the very important pillars of energy security of the world. So if you look at solar energy, the solar flux that is yearly incident upon us is nearly 3.8 million exajoules. I gave a figure of 3.4, but these figures are a little variant from one another, but roughly you can say 3.5 million exajoules of energy. In comparison to wind, in comparison to solar, you can see wind biomass are much smaller. So the amount of solar energy that reaches the surface of this planet is massive. It's 1.7 into 10 to the power 17 watt in terms of power, and as somebody quoted, in 1 year it will be about twice as much as will ever be obtained from all of Earth's non-renewable sources of coal, oil, natural gas and mined uranium combined. So there is a tremendous potential for conversion of solar energy into electricity, provided we are able to harness all of it. So if you look at the map of the world in terms of, so this is provided by, you can go to this website http://global-solar-atlas.info, and this is published by World Bank Group and funded by a couple of agencies. This map shows global horizontal irradiation map across the world. You can see that and as you go from green to red, you can see the daily total or yearly total of long term average of global horizontal radiation increases from 2 to roughly 7 kilowatt hour per meter cube, and yearly total is about 2500 to 2700 kilowatt hour per meter cube. You can see countries like Africa, Mediterranean, Australia and certain parts of South America and western part of US or Mexico, they are very well endowed in solar radiation. They are in dark red color. India, somewhere here, so we are here, we are not in dark red region, but we still get irradiance of about, daily irradiance of about roughly 5 to 6 kilowatt hour per meter square, and this is a good enough number to meet our energy needs, and especially this western part of India, which is the Gujarat and Rajasthan region, it is very rich in radiation. Also certain parts of Tibet and Ladakh, they are very well endowed with solar radiation. So we have good solar potential in the country, and this can be translated into photovoltaic power potential, and one can get a long term average of photovoltaic power potential or output power daily. On a daily basis we can get roughly, in the context of India, anywhere from 4 to 4.5 kilowatt hour per kilowatt peak of solar power. This, if you multiply this by amount of energy that is needed, by the amount of solar installations that are required, and translate that into area of land, it won't be a very large amount of area within the country to meet our energy requirements. So this is a blown up map of India. You can see in the western part of India, especially this region, is very rich in solar energy. Similarly, eastern part in the northern India, in Ladakh, is very rich in solar energy. In comparison to wind, if you look at, wind has high speeds in this area, in western part, and in certain parts in southern India, whereas in the rest of the India, the wind speeds are not high enough to lead to large scale wind installation. So solar energy potential for India is significantly huge, and this has been estimated by Ministry of New and Renewable Energy, and as I will show you later, that the potential of solar energy is far more higher than other technologies. So there are two kinds of solar technologies. One is active solar technologies, which use things like photovoltaic panels or pumps or fans or solar thermal correctors to harness the energy, convert it into useful energy, and these are called as supply side technologies because they increase the supply of energy. And there are other technologies which are called as passive technologies, wherein we use the materials or design of house, etc., to maximize to harness the sun, such as by positioning the wall with respect to sun appropriately, etc. In this lecture, in this class, in this course, since we have been talking about photovoltaic technology, it is an active technology, and this is what we will be talking about. So there are multiple uses of solar technologies. You can use it for architectural planning, urban planning, solar lighting, solar thermal, for heating, for water treatment, for cooking, etc. You can use it for electricity generation using two methods, as I talked earlier, using photovoltaics and solar concentrators, and this is what we will focus on in this class. and there could also be solar chemical methods and solar vehicles. So, multiple methods of solar energy, but we will be limiting ourselves to the discussion on solar photovoltaics. So, as it has been estimated by NICE, National Institute of Solar Energy, which is a wing of Ministry of New and Renewable Energy, the solar energy potential in India is about 750 gigawatts, which is much larger in comparison to wind energy or bioenergy or a small hydro, and that is why it is very attractive, because it can help us meet our future energy demand. And total renewable potential for India is more than 1000 gigawatts. And the roadmap for renewable power is that India has already said that by 2030 we would want to produce 500 gigawatts of electricity from renewable sources, and it made a promise in the Paris Climate Agreement, and so we are projected to move on the path of solar energy and other renewable energy technologies in a very fast manner. So, India's primary energy consumption is going to increase quite rapidly. There are three scenarios. There could be combination of composition and technology assumption. There is more growth in manufacturing. There is slower industrial technology improvement. Depending upon which of the scenario you take, your consumption could be higher or lower. We are looking at figures of around 150 to 160 quads of energy that could be produced using renewable power. And there is also significant competition between, because a lot depends upon the economics in the market, and as the world energy outlook suggests that the future for solar PV or photovoltaics is far more brighter as compared to other technologies. The rate at which they are going to grow will be far more rapid as compared to other technologies. Wind is also going to grow quite faster, but you can see that the solar growth is projected to go beyond 3000 gigawatts as compared to other technologies across the world. So, this is where we will stop for now, and we will now focus on solar photovoltaics and solar radiation in the next lecture. We will close this lecture here. Thank you very much.